This meeting is being recorded.
So, schedule reminder, 5 weeks left. 1, 2, 3, 4, 5. It's not many. You need at this point to be making a detailed schedule of what you're going to do each week to be able to finish on time. So this week is software, interface applications. Next week is wildcard, where you pick the assignment. And then we've got 2 weeks or 3 weeks on broader context, not introducing new technology. So this week is about building software applications, not on the embedded device, but on interfaces to users. So the individual assignment is to write an application that interfaces a user with an input or output device that you made. And the group assignment is just to compare options. I'm going to cover lots of them. And a nice example was Nadi, who is a designer data analyst, and she did an amazing tour this week of every possible option. So these were all examples. Well, actually, why don't we take a minute and show them? She did lots of different examples of ways to interface data and visualize it. So here's a 3D world showing the data. This is streams of sort of fireworks showing the data. This is sort of fur showing the data. Your eyes will sort of glaze over as I scroll, just because she did so many. She used every possible tool to visualize data. And this is a really fun, expressive week. More than a simple graph, really interesting ways to look at interacting with your devices. So you're going to be building desktop applications, or when I say desktop, it can be desktop, tablet, phone, but applications to interface to embedded devices. I've shown you some in previous weeks, just in my examples. Now you're going to write them. So first, I've been saying hello world. You've heard that term. Hello world dates back to the original C language many years ago. And this little tiny program prints hello world. And ever since, that's become a basic concept, is just saying hello world is the simplest thing. And so this is a page that collects 600 different hello worlds in all of these different languages. So there are many languages available. In addition to sort of the conventional languages, there are also, this is a page about perverse, bizarre, odd languages. And there's quite a community of them. So to start, you need to pick a language. You've been writing C if you're using Arduino IDE, you're writing C. It's C++, which is C. You describe the steps. C++, extended C with objects that can link types of data and methods that go with the data. So you can use C on the desktop, and there's some cases where I want particular performance, and so I'll write C on a desktop. C# is you could call it a successor to C. It came from Microsoft as part of a .NET framework. I wouldn't recommend starting with it from scratch unless you're already in a context using it. Then this next group of languages all emerged because C lets you shoot yourself in the foot, meaning in C, you can write programs that have memory leaks and get worse over time. You can have buffer overflows where data goes beyond where it's supposed to be. It can crash the program, but it can also introduce security vulnerabilities. You can have what are called race conditions, where what happens is not deterministic based on the order of different things executing. And so there have been a number of languages that were developed to get around not the performance, but the safety and security and stability of C. And these are all maturing, different groups supporting each of them. No single one has won, but they're all maturing. These are functional languages where instead of describing steps, you describe relationships and functions that have passionate programmers. These are scripting languages. So when you type commands in a terminal, the most common terminals know how to use these. And so I'll often write little programs in scripting languages to automate typing commands. Perl and Ruby are spiritually and in the same domain as Python. I'll talk about a lot about Python in a minute. APL is not a modern language, but it's one of my favorite languages. It was developed as a way to do math, not simply program computers. And the idea, it's a completely different notation, but it's a powerful notation that lets simple expressions do very complex things. And it's actually maybe my favorite language historically. And so then we get to Python. Python was developed to take the best elements across all of these. So to take, let's see, there's a request to start AI companion. I started that. Python takes the object structure of C++. It takes the kind of Lisp processing of Lisp as a language. And then it's not widely appreciated, but it takes the sort of operations you can do in APL. And so Python is a beautifully designed language. It runs on anything bigger than a little processor. It's very well documented with its own documentation. One issue with Python is this is a cartoon over when you're writing Python, you're importing libraries, you're bringing in modules, and there are multiple different frameworks to do that that are internally inconsistent. And so I use Conda as a package manager for Python is what I recommend. PyCharm is a development environment specifically tuned to Python. And so I strongly, for many reasons, recommend Python as a programming environment to learn on the desktop. And as we get to graphics and things like math and high performance computing, I'll show you lots of Python examples. If you like the Arduino IDE, you'll like processing because of the lineage. So processing, Arduino emerged as processing in embedded devices, but going in the opposite direction. If you are comfortable with Arduino, processing sort of feels like Arduino, but on the desktop. And then P5.js is a JavaScript library roughly compatible with that. So just for the sake of a language itself, I recommend Python. If you're already comfortable with Arduino for embedded stuff, you can use processing to build desktop applications. Java was a language created to compile in a way that has an interpreter that then runs on every platform. I wouldn't recommend Java unless you know you need to use it, given the other language options. JavaScript, confusingly, has nothing to do with Java. It's just a historical naming. JavaScript Python is a beautiful language from scratch. JavaScript was written to do scripting in the browser. It was just a hacked language for scripting. It's not a beautiful language. And the original version has all sorts of limitations. But given the importance of the web commercially, lots of work has gone into the performance of JavaScript, and it's gotten better. The language has matured a bit, and so it's gotten better with some of the things originally missing. So if JavaScript is the language you use for web applications, Mozilla runs a site for documenting it, MDM. It has both good documentation and tutorials. JavaScript runs in the browser. There's a number of security limitations. Node lets you run JavaScript outside the browser and just build standalone JavaScript applications. V8 is one of the engines. And what this does is just-in-time compilation. So you write JavaScript. When you execute it, just in time it gets compiled, and it gets compiled very efficiently. You'll see this when I go over performance, but it runs very effectively. NPM is a package manager for JavaScript. And let's see, I'm looking at the the memes in the chat. NPM is a package manager for JavaScript that has some slightly messy history, but is a package manager for it. WebAssembly is a newish thing that lets you compile other languages down to a very, WebAssembly, that link is broken. So WebAssembly, okay, so that's moved. I'll fix that link. This lets you compile other languages into things you can run in a browser, and that's maturing. So for building web applications, I would learn JavaScript. Then this next group of applications is what's called data flow. So in all of these, for example, in App Inventor, what you do is rather than writing lines of code, you make a picture of how information flows through it. Blockly is a nice framework a general purpose framework for creating your own block-based applications. And so these are all versions in different domains of data flow. And now I'll focus in on two of those in more detail. So Node-RED came from IBM, and it's a open data flow framework for building applications that interface with embedded devices. And then mods that I originally wrote, you've been using it possibly to do toolpath generation, but it's a more general data flow environment. So I'm going to go through an example that shows lots of different things. So this is a C3. I've gotten a button and an LED. And I'm going to talk to it multiple different ways. So the first thing I'm going to do is, let's see. This is the embedded code in the C3. And so in the embedded code, I have, I'm going to use Microdot as a framework for web serving. And again, this is the embedded code. I'm using async IO that lets me do what's called cooperative multitasking. So I have multiple tasks running, and they decide when to take turns. So one task is to interface with the button. One is for web serving. And so the local task checks to see if the button is pressed. And then it says, I did my job. You can do something else now. And then the web serving task checks to see if there's a web request. And if there is, it uses it to turn the LED on and off. So that's what's going on in the embedded code. So now if I go here, I'm going to start it running. And if we go to the embedded code, you can connect to an existing access point, or you can be the access point. Here I'm connecting to the existing access point, and you have to tell it the SSID and the key. So I've now got my embedded code running, and here's the address that it's at. So the first thing I'm going to do is I've got a web page here, and this web page has some buttons. And the first thing I'm doing is I'm interfacing to a Node application. So this Node application has a WebSocket server. And with the WebSocket server, then this web page, what the web page does is a WebSocket lets you pass messages to and from a web page and a server. And so the web page is putting up some simple interface elements, and it's using a WebSocket to send and receive messages. So initially what I'm doing here is the web page is doing it to a Node application. Now I'll have the web page do it to the shall. And so now with the web page, I'm pushing buttons on the web page, I'm turning on the light, and the web page is updating as I push the button. So in that, let me pause here. So in that example, I wrote a web page, and I just wrote the code in the web page to interface to the shell. Now I'm going to do the same thing in mods. So mods has modules that generate events, has modules that show events, and has modules that talk to WebSockets. So here in mods workflow, I'm going to connect with the WebSocket, and now I'm using mods to generate WebSocket events that turn the LED on and off. And when I push the button, I get a message down here. So now instead of making lines of code, I'm making a graph of how information flows through it. And then I don't need anything to run this. It's just a mods workflow. And you can export from mods to, you can save it as HTML. So I just save that mods workflow as a HTML page. Now I'm going to go to Node-RED. So Node-RED is a framework for building data flow app interfaces. I'm going to start a Node-RED server locally. Then I'm going to connect to my local Node-RED server. And then I've opened what they call a flow. And this is just showing the configuration I'm using. So in this flow, I've got modules that create events and send them to a WebSocket. And then I've got a WebSocket that comes to something that let me see what's coming in. So when I start this running, I push the LED and it turns the light on and off. And I push the button and it tells me I'm pushing the button. So all of that was, you make a diagram of the elements you're using. And then the graph is running the code, and then it builds the UI on top of that. So yeah, Node-RED has matured nicely. It's a clean environment for building data flow applications, and it knows how to talk to all sorts of protocols in and out. So that was using both Node-RED and mods to do data flow programming. You've already likely been experimenting with ChatGPT. Copilot is a AI tool trained on GitHub. Both of those can help you write code. Both continue to trip over issues like code that's almost right but has some mistakes, and copyright and licensing issues. So that they're rapidly evolving, but maturing. And then you'll also run into terms low code or no code. And those are environments to build application without having to know much about writing application. And Node-RED is roughly a version of that, where you just drag in some easy to use blocks, and then it, under the hood, it builds everything you need to make it work. So I would recommend learning Python. Is probably the nicest of all of these languages. I'd recommend learning JavaScript for web programming. And I'd recommend learning one of the data flow frameworks like Node-RED or mods to learn how to do visual data flow programming. I use all of them. No one covers everything. I use Python when I'm limited by algorithm complexity. I use JavaScript for stuff that's just native from the web. I like to use these to quickly throw together applications with easy assembly of the code. So they're all useful. I would look at each of them and see what works for you. And also, yeah, if you're already happy with Arduino, look at processing in P5.js. No one is best. Experiment with them, see what works best for you. So after all of that, you have a language you're going to use. Then we need to get from the application to the device. So we've been using RS-232 commonly. So PySerial is Python to serial. Node can talk to serial ports through a serial port, and then web serial, that's Chrome family browsers, talk to serial ports. If you're talking to I2C devices, Python, Arduino have I2C interfaces. If you're using USB, we use it with profiles, but these are libraries to talk to USB directly. And let's see, this list is something of a mess, which is IFTTT, XMPP, UPnP. These are all frameworks for how devices that don't know each other can learn how to talk to each other. Let me save a note. So there are many of these frameworks of how different devices talk to each other. None of those are really, no one has critical mass, but what has gotten critical mass is MQTT. So I'll spend a while on this. So the problem MQTT solves is, let's say you're AgriLab and you have a farm. You have many different sensors in the farm, and you want to know what the sensors are. You have actuators, like things to control irrigation. And then you want to visualize the data, and then you want to implement controls so that, like, when the things get dry, you add irrigation. And so how do you manage that cloud of devices? So MQTT is a framework to have lots of different network devices be able to talk to each other. And it's simple, lightweight, easy to understand and use. MQTT, Mosquito is a broker for MQTT. It's one nice implementation of it. And so I'm now going to go through an example of using MQTT to interface to the device. So I've got a lot of things going on here. So in the lower left, this is showing my MQTT. I'm going to start an MQTT broker. So I had posted, let's see, let me, you have many different devices that do different things, and the broker is what hosts the communication. So you can send messages into the broker and you can get messages out, but the broker is at the heart of an MQTT system. You can run one locally, and then for Fab Academy, Julian set one up. And so this is an address with a username, password, port, and channel for an MQTT broker. Luis is asking, can you use MQTT without a broker? Sort of without MQTT, without a broker, you need a way to figure out who talks to whom. If you just want to send a message from here to here, remember sockets. You can send UDP, lets you just, if you have two devices and you want to send a packet between them, socket programming with UDP lets you do that. And back on this page, I skipped over it because I talked about it before, but here's in Node and in Python socket programming. So you can use a socket to send a message. The problem is you need to know who needs to send the message to who. And again, that's why MQTT exists. But you can just send a message through a socket if that's all you want to do. So this is a central MQTT broker we're running that you can use for the class. Here I'm going to run one locally. So I'm going to start up an MQTT broker. So I'm now running that. So now if we go to this is the embedded code, and for my embedded code running on my shell, I'm going to be running an MQTT client. So it needs to know the server I'm going to talk to. I need to connect to the network. And then I connect to the broker. And then the heart of MQTT is there are channels that are sort of like channels on your TV. And you pick the channels. And then there's publishing and subscribing. So you can subscribe to follow messages on a channel, and you can publish to the channel. So on my embedded device, I'm going to connect to the broker. I'm going to subscribe to the LED channel. And then if I get messages on the channel, I'm going to publish responses to it. So that's what's going on in the embedded code. So I'm going to start that running. Then what I just did is my shell is connected to the broker, and it's subscribed to the LED channel. Over here, I'm just typing commands in a terminal, and later I'll show you how to do it from a browser. Here, I'm going to publish to the broker on the channel LED a message turn on. And now I'm going to publish the message turn off. Those are both to the LED channel, and I'm sending the message on and off. Now I'm going to, instead of publishing, I'm going to subscribe. And I want to know what's happening on that channel. And so now when I push the button, because I'm subscribing to the channel, I get the updates. So I've got the broker running. So let's see. In that example I showed you, I've got the shall. I've got the broker. And then I had the terminal. And the shall connected to the broker, the terminal connected to the broker, and I both sent messages out and got messages in. Now what I'm going to do is do that in a web browser. So if we go back to here, this is a implementation of MQTT in JavaScript I bring into the browser. And so in the web page, I can connect to the MQTT broker, and then I can do the same functions. So now, so now I just click connect on the web page. The web page is connected to the MQTT broker, and I need to know the address and the port. Now, when I push the button, you'll see the message came out. So if we go over here, now I've got the web page. The web page is also connected to the broker. So if I push a button and it goes into the LED channel, a message goes out to everybody subscribed to that. So when I push the button, you'll see the message appears both in the terminal and in the browser. And then I can push the buttons on the browser and I control the LED. And since I'm subscribing down here, I'm also seeing that. So that example showed I've got an input and an output on the board. I've got a browser and a terminal. And then the broker is coordinating all of these to talk to each other. And let's see, Luke is showing an AgriLab example of using LoRa as the transport, as Wi-Fi over longer distances, and then data coming in and graphing it nice. So MQTT has really matured, has critical mass, it's stable. And in particular, what I like so much about MQTT is it's not cluttered. It's conceptually just really simple. There are channels. You create whatever channels you want on the broker, and then you subscribe to see what's happening on the channel, and you publish to send information to the channel. And it can be one to many. One message can go to one publish can go to many subscribers, or it can be many to one. Many publishers can go into one subscriber. And that's really what MQTT does. I'd say the biggest limitation is there is the overhead of talking to the central broker. And so there's been a fair amount of work on the performance, but if you need, say 10 millisecond response, it should be fine. If you need stuff happening faster than a millisecond, you'll be pushing the limit of just the performance of the MQTT broker. But for something like Luke's farm, you're likely not to be limited to, to that very high speed, high bandwidth. And so MQTT gives you a really nice structure to do it. So once again, Julian just set up an MQTT broker available to anyone in the class. These are the authentication for it. It's also very easy to set up your own MQTT broker to run it locally. Yeah, Leo's noting cheap RGB light bulbs learning MQTT. So I recommend experimenting with MQTT for this week. It's a really nice framework. It's powerful. It's general. It has traction, but simple, and it's a nice way to coordinate talking across multiple devices. The central server broker is convenient because you don't need to do anything. On the other hand, you'll pay latency going out to it and back. It's very easy, as I showed in the video, to run a local MQTT server, and that improves the latency to talk to it. Okay, so you've picked a language, you've picked a way to talk to your devices. Data is going to be coming and going. If we look at Luke's farm, well, actually, yeah, this is a nice example. Let's go back to that. So here's data. How do you handle that data? Where does it go? Simplest thing to do is just write the data to a file. And that's actually a reasonable thing to do up into roughly the size of your computer memory. And I'll talk about that when I get to databases. But that's just lines. It doesn't really have any structure. JSON is a way to structure data to describe objects in files. TOML is a descendant of that. That's a very clean syntax. And so if we go to the Fab Lab inventory, this inventory looks like a spreadsheet, but the underlying data is just a TOML file. So if we go into here, this is the inventory itself. It's a structured file where we put in these names, and then that turns into objects, and from those objects we can then do things like make the inventory spreadsheet. So TOML is a way to do that. You can use spreadsheets. They're not really good for handling large amounts of data. And then SQL and Mongo are databases. And those are storehouses where you can request data with a key and get data back. You don't need these for small amounts of data. Where you really need these is where the amount of data is so large you can't fit it in the memory of your computer. And so you need to store big repositories. For smaller amounts of data, you can use things like TOML to structure it. For simple things like just readings, you can put them in a flat file. You need databases when you're dealing with much larger amounts of data. Okay, yeah, just chat about stability and security of relying on these things. Okay, so a little bit on storing the data. Now we need to build user interfaces. So curses is something I'm very fond of. Curses is when you use a terminal, terminals can actually let you, let's see, I don't think that's just an ad.
Hey, what's up, YouTube?
So
It is for the splash screen where you
Yeah.
have the option to look at.
So this is doing 3D. This is a 3D game that's just running in a text terminal, and all it's doing is putting characters on the screen. So curses lets you put characters on a screen, which is seems crude and old-fashioned. What's nice about that is it's very low data rate and needs minimal things to show it, just a terminal. Just good to know about that. In Python, let's see, let's go to schedule input devices. Let's say do temperature. Here's where I showed the temperature reading. And that's using TK. So TK is a widget library, and tkinter is the binding for Python. And so if we look at the Python code, what this lets me do, so I have to read it in. This lets me create a window. Then I'm going to make a drawing canvas. In the canvas, I'm going to put up some graphical elements and a text element. And then as I get data in using PySerial, down here, I update the graphical elements. And then I'm running what's called an event loop, where I tell it, after I update the graphics, call me again when you can. Rather than running it, if I run it continuously, I'd be fighting with what else is happening on the computer. This cooperates gracefully. This says, keep calling me when you can. And so with that, that then puts up the window, puts up the bar graph, and updates the numbers. So TK is a widget set. That's an example with Python. And the advantage of it is it runs just about everywhere, and looks the same everywhere. On the other hand, the disadvantage is it doesn't really look like a carefully tuned native application. It always looks like a TK application. So Wix is a family of widgets. And again, widgets are like buttons, sliders, knobs, dialogues. Wix is designed to look local to the OS. This is bindings for that. Qt is a widget set with an interesting history. GTK, Clutter, these are all widget sets. They all work. They're all powerful. Let's see, Hank is showing these dashboards as a way to quickly visualize. And then something I'm a fan of is one of the oldest parts of the HTML spec are forms. This dates back to the beginning of HTML. And when you fill out a form, you need some basic interface elements like dialogues and buttons. And so if we go back to this MQTT example, the web page up here isn't using a library. It's simply using HTML form elements that any web browser knows how to use these basic form elements. And likewise, that's what I use in mods. If we take a mods, all of these elements you see here, these buttons and controls, these are all just part of HTML forms. And so what's nice about that is it's a lowest common denominator. It loads quickly. You don't need any libraries with it, but you can do much better than that. So jQuery, DAT-GUI, Bootstrap, Flap, Material, these are all nicer looking widget libraries. You need to bring in the libraries for them. This is all for JavaScript, but are more modern looking interface elements. This group are all things where, so far I've just been showing you something where it all works in one web page. When you build more complex applications, you have multiple packages and you have multiple JavaScript routines and multiple files. And then you need to coordinate the dependencies across all of them. And so these are all frameworks to handle dependencies for more complex sites. And then this long line that's evolving fairly quickly are all attempts to solve the same problem, which is you can build an application that runs on a full desktop screen. You can build one that runs on a tablet. You could build one that runs on a phone, one that runs on a watch. If you want to run it on the phone, it might be an Android phone, it might be an iOS phone. And so these are all attempts to build coding environments that let you write your code once, but present it multiple ways across multiple platforms. No one of these has won. All of these do a version of that. So these are ways where you don't need to redo your code to target different platforms, but write it once and be able to run it many ways. Okay, so those are widgets to let the user interact. Then often you want to do graphics. So I'll skip X and Java as being historical. For web graphics, what I'm now going to show you is the same thing multiple ways. So here I'm animating. This is sine of X over X, and I'm varying it. So I'm animating lines, and I'm animating, I'm doing that as images. So that's using Canvas. Canvas came from, it was an Apple extension, and this lets you do bitmaps on the screen. So this is JavaScript. Canvas is now part of the standards. And so I have to get a context for drawing into the so I have to create a canvas. Then, oh, sorry, I'm saying this in the wrong order. In the web page, I create a canvas. In the JavaScript, I get that element. I get what's called its context to draw into it. And then all I'm doing is I'm pushing pixels to the screen. So here I clear the rectangle, I draw lines, I stroke it to say push it out, and then I animate that periodically. So that's in 2D, and in 3D, it's similar. I get the canvas, but now what I'm going to do is instead of drawing lines, I'm filling a buffer with an image, and I'm pushing the image out to the screen. So Canvas is good if you just want to push pixels on the screen. This is going to look the same, but it's very different. So SVG is a beautiful standard for 2D graphics on the web. And what's different about this is in SVG, so in Canvas, there's just dots on the screen. In SVG, objects have an identity. So here what I'm going to do is I'm going to create a line, and to animate it, I'm not, in the canvas, I was redrawing it from scratch. Here what I'm doing is I'm updating the coordinates and I'm moving the line. I'm not redrawing it every time. The line stays on the screen and I move it. And so that's nice if there's multiple things on the screen, you don't have to keep redrawing it. And it's also resolution independent. The canvas is just pixels. SVG looks the same. However I zoom in and out, it's resolution independent. So SVG wins if you have objects you want to manipulate on the screen. Then WebGL is a standard for 3D graphics. It's low level, and I don't recommend starting with it. 3JS is a high level wrapper around it. That's what's called a scene description language. So here's a 2D version, and it looks like what we've seen. Here's a image version. It looks like what we've seen. But this one is the most interesting one. Here's now a 3D version. So I'm drawing my data as a 3D surface rendered in the browser. And that all of that's using 3JS. So to do that, I need to load the 3JS library. A canvas and SVG are already built in. Then it's a scene description. So I make a scene. I have to put a camera in the scene. I have to tell where the camera is. Let's see. There's a question about all of the examples I showed. That was the featured example. If you go to this week's class interface and go to the end, and click on assignment, that'll take you to her. So I have to tell where the camera is, what it's looking at. Then I have to put objects in the scene. And here I'm going to put in, there are different sort of primitives. Here I'm going to put in a plane. And then this surface has vertices, the points on it. Then here I'm going to describe the material properties. I'm going to put lights in the scene. And then I have to add a renderer to be able to render the scene. And then when I animate it, I update the vertices. And then I have to tell the renderer to update what it's looking at. And then I update the animation. And so all of that gives you this. Now, as a note, I don't remember how to do this from scratch. That's a fair amount to set it up. So I always start by modifying an existing program. And if you go to the 3JS site, they have tons of examples of how people are using it. So if you want to buy a few $100,000 car, you can do that with 3JS. But the other thing they have that's great are the examples. And so each of these examples, this is a complex, crazy 3JS world. Each of these examples shows a different attribute of 3JS all running in the browser. And so you can browse through the 3JS examples, find starting ones, and then plug those into your data interfaces to do beautiful graphics. And in fact, these examples show you can use 3JS in with lines, with 2D images as well as 3D. The reason to use it, even if you're not doing full 3D graphics, is it interfaces very efficiently to the graphics hardware. And so it gets data on the screen very efficiently. So that's 3JS. If you're writing Python, here I'm doing that same 3D graphics, but now I'm doing it just directly from Python. So I'll talk about NumPy in a minute. Here I'm using a library called GFX, and it's a scene description language. And so that very cleanly lets me write a Python program that makes 3D graphics. And then here's the same thing in Tai-Chi. Tai-Chi is a framework for accelerating Python I'll talk about. And again, this lets me very easily do 3D graphics in Python. And the last note is the game engines are all scriptable. This was showing from before where I used the physics engine in Blender. you can script the Blender and the game engines and use them to do visualization. Okay, that's 3D graphics. For sound, for audio and video, SDL is a cross-platform multimedia interface. These are bindings to it from Python that let you play sound and play videos. Open Frameworks is a media framework. This is a Python binding. These are all versions of media frameworks with bindings. And then crucially, HTML5 in the history of the web added audio and video to the web. And so this version, here, let me get into my sound settings for this one. So let me get that ready. So here, I'm gonna crank this up. So I'm gonna be quiet and just listen for a second. So you hear a thump. That thump is, I'm taking sine x over x again, but I'm playing it as a sound. So in the web page, I get an audio context, which is part of this HTML5 extension. Then I'm going to fill a buffer with sound, and I push the sound out, and I queue it up to the audio context. Remember, we had the drawing context for graphics. The audio context is what I'm going to use to make sounds, and I push the sound out. And so with that example, you can have a web page that sonifies, that makes sounds based on what's coming in. And then WebRTC is in input devices. I had showed this example of in JavaScript connecting to a camera. And then what I'm doing is I'm streaming video to a web page. And so if we look at that HTML, here what I'm doing is I'm connecting to a camera and using it as a video source, and then I'm streaming video out. So along with these media frameworks, just HTML itself knows how to talk to audio and video in and out. So hey, then virtual reality is where you go into a virtual world, plugging your senses. Augmented reality is where you look at the real world, but you augment things that aren't there with things that are there. And then MR, XR are variants of mixing all of these. And there are multiple frameworks for these emerging. I'd say the most useful thing to know is if you use 3JS, 3JS lets you immediately export to VR, so you can talk to a VR device. And then 3JS also knows how to talk to AR devices. And so if you build something in 3JS that works on the screen, you can then turn it into something that works into VR goggles and something that works on a phone overlaid as augmented reality. So there are multiple emerging frameworks for these, but in particular, conveniently, 3JS knows how to do all of that. So you've built an interface. Let's see, you picked a language, you built an interface, you've got data. Then there are a number of reasons why you're likely to want to do things with your data. You might want to, if you want to know when you need to irrigate on the farm, you need to analyze the data and find, you might want to remove noise, look for features, find where triggers are. So I strongly recommend NumPy is a Python extension for doing math. freely available cross-platform. Matplotlib is a set of Python libraries for visualization. So here's a graph of sine x over x, and in NumPy, it's comically simple. So this imports the plotting library, imports NumPy. This creates a vector of values, a list from -L to L. Then x isn't one number, it's a list of numbers. And so what this line does is it evaluates sine at each of those numbers and divides it. And then this plots it and shows it. So that's all I need to make a graph of my data. I can animate with this, just like I've been showing you. And so to do that, it's only slightly more complex. I get handles for the figure, and I can redraw the figure. I can do it with images like I was doing it. And here, it's this little loop. I make vectors. This makes an array. I do the math on the array, and I redraw it. And in fact, I can do the 3D plotting just as easily with just this little bit of code. So NumPy and Matplotlib are beautiful frameworks to do math in Python. Then Anaconda lets you make notebooks, where instead of having a program that just gives you output, you can have little bits of code mixed with their output and make interactive notebooks. And these little bits of code are Python code, so they can talk out to all of the different sensor interfaces. And so you build a notebook of both the code, what it presents, and your commentary on it. Let's see, less relevant here. These are libraries from symbolic math. These are math libraries in JavaScript. This one is relevant. Here I'm making a graph in a web page, and that's using what's called Plotly. So this is now JavaScript. I've pulled in the Plotly library, and instead of doing SVG or Canvas, I'm using Plotly to make a graph and update it. So Plotly lets you, you can use it in multiple languages. So you can use it in Python, but crucially, you can use it in JavaScript. Then, so far what I've been showing are fairly conventional ways to present data. If you look at all of these, this is more related to what Nadia was doing. These are all really interesting visual representations of data that aren't simple graphs. So this is a lovely library for presenting information in really interesting, creative ways. Okay, and then last in the math sequence is we've talked a bit about machine learning. PyTorch is one of the main frameworks for programming machine learning. TensorFlow, that's heavily used in research. TensorFlow is slightly older, heavily used in production. There's a port of TensorFlow to JavaScript to do machine learning in JavaScript. And what I've done here is a teeny example, but it shows the essence of it. So, you know, an XOR logic gate has the truth table 0, 1, 1, 0. So it takes two inputs in, it makes one input out, and that's how it does it. And so the simple example I'm going to show, which happens to be historically important, is if you were looking at a device and you didn't know what was in here, all you could see was the inputs and outputs. And this is trivial for 2 input, 1 output. But for that simple example, is if all you could do was see inputs and outputs, and you had to train a machine learning model to predict the output from the inputs. This is non-trivial when there are many inputs. I'm going to do it for the trivial example of just 2 inputs. And so what I'm showing you is a PyTorch model. So this is my input data for training. This is the output data. Then I'm going to make a network with layers. And in classes, this is a class I teach on mathematical modeling. I'll put this in the chat. And I'm updating the notes of a textbook for this. And in the notes on machine learning architectures, I explain all of the different options that go into these architectures. But here what I'm doing is I'm making a network that has an input layer. It has what's called a nonlinearity. It has an output layer. I initialize the model. Then I'm going to train it on the data. And then I run a training loop and present the output. And so what it shows is, this is showing you the error as it's training, and then the final results of learning how to do that function. And so it's far beyond the class to go through all of these, to really explain each of these. But this shows you the basic structure of, you bring in data, you have to define a model architecture, you have to initialize the model, you define how you're going to train it, then you train it, and you see the output. And those are really the elements in just about all machine learning cases. And so that's an example of, you could do it in a browser with TensorFlow.js, offline. I mean, in Python, you can do it with PyTorch, of training a machine learning model. Now, this link goes to, over many years, I've done a simple task, which is I sum this formula that calculates pi, and I use it to measure computer speed. And so if you look at this table, this column is billions of floating point operations per second, called flops. And this dates back to a ancient early Intel chip, and it's 0.000001. Then as we go through, you'll see some of the microcontrollers you're using, along with some historically important computers. And then if we go to the other end, this is 17 petaflops on one of the world's biggest computers. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's about 13 orders of magnitude difference in performance. So as you progress, you might end up caring about the speed of your code as you do more complex things. So Python itself is slow. It's interpreted. Numba is an extension to Python that compiles it to make it run faster. JavaScript is fast because it's just in time compiled. But in addition, what it can do is, here, I'm going to calculate this. Sorry, let me do that one here. So that was 3 megaflops, gigaflops. That was 5. Now it's 10. I'm running on a multi-core computer, a computer that has multiple processors. And what this is doing is, it's doing the calculation using multiple processors. Let's see, Leo is asking, can Numba compile MicroPython? No, MicroPython itself knows how to do that. MicroPython has a decorator native that does something like that to compile. So the native code emitter is the embedded version of that. Then let's see, these things are GPUs run dramatically faster than CPUs. And so these are ways to program GPUs. And then Tai Chi that I mentioned before for graphics is an accelerator that lets you write Python code, and it knows how to accelerate it. So you can run it on multiple cores, or you can run it on GPUs to run it many times faster. So roughly, Python, well, actually here, let's do this really quickly. If we go back to this list, so in gigaflops, this is all a desktop computer. The Python by itself is slow, 0.02. C on that same computer is 10 times faster. C, if you tune the performance, is 100 times faster. That's about the speed of JavaScript. But then that's the speed of Python if you compile the Python. But then if we write it not for the CPU, but for the GPU, it's about 1,000 times faster. And so this is just a tour through the ways to make code go faster. Once you're done writing your code, if you want to deploy it, then these are links into cloud services. So when you're using Fab Cloud, it's running in an instance in one of these cloud data providers. These are links into it. I won't take time for that now. This is a tool that, rather than running a server in the cloud, lets you deploy applications directly to the cloud. These are some notes on security, and I won't do that now because I'll be talking about that in the system integration class. So I won't take the time for that now. But stepping back from this tour, I just covered a wide range. The goal for this week is for you to find where you fit here. So learn Python is a beautiful language. Learn processing if you like Arduino. Learn JavaScript if you want to write for the web. Learn about mods or Node-RED or some of these other options if you want to make data flow graphs. Experiment with how you talk to the device, and in particular, if you want to talk to multiple devices, learn about MQTT brokers. Learn how to build user interfaces with widgets and graphical elements. These are options to display images. These are options to make sounds and do video, to augment, to begin working with the data, to accelerate. And as a group, just compare as many of these options as you can. As an individual, you're going to write an application. You're going to interface a user, most likely you. And then for this week's assignment, I want it to be an input or an output device that you made. So not an arbitrary thing, but take one of your earlier input or output devices and build an interface to it. And then finally, with our rapidly receding time, try to target towards your final project. Figure out where you need an interface. And again, when I say interface a user, it's designed for something, a higher level interface, like a phone or a tablet or a desktop computer into an embedded device. So this class might have the broadest range of options. You don't need to master all of that. What you want to find is the parts of those space where you're happy. And you have fun with this class. This is also one of the most expressive classes. You can build really expressive ways to present data, to build user interfaces personalized to you and your application. So with that, I'll be posting the education recitation video. I'm just back from travel. So in the next day or so, I'll get to that. No recitation this week, but as usual, open time. And please start, if you haven't, using your final project page to log your work. And please make a schedule for the remaining weeks to get you ready to present on time. Oh, education is already on the YouTube channel. Good. Okay, so that's interface and application programming. Happy programming. I look forward to seeing what you do next week. Bye-bye.
Bye-bye. Hasta luego.
Bye. Bye.
Flash factory killer.
Bye.
Ciao.
Bye. Good night.
Hey there.
Slang.
Assalamualaikum.
Bye.
Ciao.